Using that general formula to find a Taylor polynomial of given degree for f of x at a given point. This is part 2 of the video. So our function this time is cosine x. We're told to find a Taylor polynomial of degree 4 centered at x equals the point pi over 2. So we do our usual derivative sequence. Then we evaluate derivatives at the pi over 2, and we get our answers. Now we notice we have a 0, 0, and a 0 here, which means that the terms are skipping every other one, and there seems to be a negative 1 to 1 toggle. So then we write out our P4, that's just the form that we have, and the coefficients are given by this, the derivative evaluated at the point 8 divided by the factorial matching up with the derivative. So then we have, plugging everything in, we have here 0 that we noticed, 0 and the 0, and we have our negative 1 and our 1 and our factorials down here like this, and based on x minus pi over 2, since the polynomial is to be centered at pi over 2. So then that all just works out to this one right here. Notice that P4 was asked for, but it's really the same as P3 because the fourth term here, the fourth degree term, cancels out with 0. So we're just going to do P3 for that one. So then we plug it into the calculator just to see where we are. Here's the cosine in the red, and our P4, which is actually the third degree, does this here, third degree polynomial. Right at pi over 2 is where it hits it exact, and then it diverges away somewhere around here and somewhere up there. Okay, so at pi over 2, the two values for this one is, this one's the f over here, and this one is the P4 right there. And so you can see they're pretty well matched up, but there is divergence even as soon as you get away from pi over 2. There is some, it just doesn't show the 4 places. So the approximation is doing pretty well. 2, you start to see just a little bit of divergence and so forth. Starts to diverge here. Really bad at 3.5, as you can see. That's where it starts to diverge really badly. So it's all making sense. So this is, we have found the Taylor polynomial for cosine of x centered at x equals pi over 2. Now what about this? What if you want to do the summation form? And we have problems like this that I put on the worksheet. What's the summation form for Pn of x for this example? So again, I just wrote down the derivatives, and I wrote down, we already did these, but I added a few more. So you can really see that there's a 0, 0, 0, negative 1, 1 to negative 1, toggling back and forth. So now we're just going to write out the terms of the polynomial and match up with the summation k counter. So this counter k in a summation has to go one integer at a time. You can't skip. So all the skipping that occurs you have to put inside the summation. So here's your summation k counter, k equals 1, k equals 2, k equals 3. And this is what has to get accomplished for those various k's. Negative this, plus all this, minus all that, plus dot dot dot. So to see what you can do, you can sort of see already that 1 has to end up being 1. 2 has to give you 3. 3 has to give you 5. The 5 factorials match up. And all you need is this -1 toggle going on. Shouldn't be too hard to do. Okay, so I just said what I said there. Right here. So here's our chart. Here's your summation k counter. Now that has to go steady by integers. And all the skipping that has to get done has to be done by some function of that counter. Here's the -1 toggles that went on. Here's the factorials that went on in the coefficients. And here's the powers. Okay, so just to get the power relationship to the k counter, here's the k counter, 1, 2, 3, 4, 5. Here's the power, 1, 3, 5, 7, 9. So a little bit of reasoning there results in the power is 2k minus 1. So for example, if k is 5, 2 times 5 is 10, minus 1 is 9. It's all working. So we can go directly to it because we can see that P3 is k equals 1, 2 to 2, but we'll see why that is in a second. There's a -1 toggle. So all I have to do is make sure this k is either k or k plus 1 or k minus 1. So if it's k, when k is 1, -1, check. When k is 2, +1, squared, +1, check. Factorial. 1 factorial. When k is 1, 2 minus 1 is 1 factorial, check. When k is 2, 2 times 2 is 4, minus 1 is 3 factorial, check. So this factorial is working, and the power always matches up with the factorial. Factorial matches up with the power, and this is your center. So this is your general formula. Now you stop at 2 because this power here is 2 times 2 minus 1 is 3, and that's how you're going to get your third degree. Even though your counter only went up to 1, it produced a third degree, and you can see why, because there's just 2 terms here that it generates. So you take the summation, check it back, generate a couple of terms, and see if that equals back to the original that you had there, which it does. So that's working. So the general term, the general form of the summation for Pn, for cosine of x at x equals pi over 2, well, I need to know where to end it. So if I want the nth power up here, if I want that to be n, to give me my nth Taylor polynomial, then I'll just set that equal. 2k minus 1 has to end up being n. I solve it out and I get k equals n plus 1 divided by 2. That's why this k counter stops at n plus 1 over 2, because when you plug that in, you'll get n. And then you have the same terms as before. And this time you run the k from 1 all the way up to n plus 1 over 2. And as long as n is odd, this works out and gives you the perfect cosine Taylor polynomial at x equals pi over 2 for any power you want, any odd power. So for example, say you want to do P23. So your k is going to be 23 plus 1 over 2. So that's going to be 12. And then this would do it. If you did that, you'll get the P23.